These notes are on writing the recursive and explicit equations, but this time for the geometric sequences, and this is what you worked on in section 1.5. So we'll do a few examples. The directions are the same as the previous notes for arithmetic sequences. Identify the common ratio, then write the recursive and explicit equations for each sequence. So in this first example, I am multiplying each time in order to get from 1 to 3, 3 to 9, 9 to 27, etc. And I'm multiplying by 3. So we say our R, which is the letter we use to stand for common ratio, equals 3. We're going to do the recursive first. Again, the recursive looks new and unfamiliar, but it's actually the way you think in your brain about these problems. You think I'm starting at 1, and I'm multiplying by 3 each time. So then I just have to fill in that funky looking notation. And that notation says f of n, the current term, equals the previous times 3. Again, this notation right here does not change from problem to problem. It's what I'm saying I'm doing next to get to the next term is what changes from problem to problem. The explicit. Now the explicit, again, you can write in two different ways. The first way is you can say, well, I'm starting at 1. And then I'm multiplying by 3 over and over and over again. Multiplying by 3 over and over and over again is the same as having a power. So I need to have a power here on the 3. Very similar to the arithmetic sequence, though, because my first term is f of 1, and I don't multiply by 3 to get 1, I multiply by 3 to get 3, I'm going to need to say, hey, look, I need to go 1 backwards, so to the power of n minus 1. Another way to do this is to say, well, I actually want to have my equation be f of 0 times 3 to the n. This allows me not to have to fix my exponent, but it does mean I have to fix the term I'm starting with. So going forward, I multiplied by 3 each time. 1 times 3 is 3. 3 times 9 is 3 times 3 is 9. 9 times 3 is 27. So going this way, we multiply by 3. So if I go backwards, I'm not multiplying by 3, I'm multiplying by 1/3. So if I want to find f of 0, I have to start at f of 1 and go backwards. So 1/3. And now I can finish my explicit equation using this method, and I can say f of n equals 1/3 times 3 to the n. And just like in the arithmetic, both of these are the same, are equivalent equations. They get us the same answers. They just start us in a different place. Example 2, 125, 25, 5, 1, 1/5, etc. So unlike example 1 where I start small and I'm getting bigger, in number 2, I'm starting big and getting smaller, which means that my R, my common ratio, is actually going to be a fraction. I am not multiplying, I'm dividing. So dividing by 5 each time means I'm actually multiplying by 1/5. And the easiest place to see that in this particular sequence is the fact that to go from 1 to 1/5, I would multiply 1 by 1/5. So now I can write my recursive. And I say, again, this is the way we often think. I'm starting at 125. It's right there. And then I'm multiplying by 1/5 every time. I'm multiplying by 1/5. And then I have to fill in that notation, and that notation does not change. It is f of n equals f of n minus 1. meaning the current term is the previous times 1/5. So now for the explicit. For the explicit, I say where I'm starting. And then I say, well, I am multiplying by 1/5 over and over and over again. Again, multiplying over and over and over again is exponents. So I then need an exponent with n up here on the 1/5. Similar to the previous example, because I don't start multiplying by 1/5 until 125 to 25, I have to say, hey, look, I don't do it to the first term. So it is n minus 1. The other way to write the explicit is to say, I want to not have to worry about my power, fixing my power. Instead, I want to worry about fixing this term. And so I need f of 0. So we say, well, f of 0 is going to equal my first term going backwards. So going forwards, we multiplied by 1/5. So going backwards, we multiply by 5. And we can see that right here. 1 times 5 is 5, 5 times 5 is 25, etc. So if I start at 125 and I multiply by 5, that gets me 625. So now I can finish this form of the explicit. F of n equals 625 times 1/5 to the power of n. Our third example is the sequence 3, -6, 12, -24, 48, etc. In this sequence, if I don't pay attention to my negative signs, we see that we are getting bigger each time. So I'm multiplying by something. In this case, what I'm multiplying, though, by going forwards is -2. So we say our r is -2. We'll start with the recursive. Remember, the recursive is the way you think about this. You start at 3. And then you multiply by -2 each time. So now I just have to fill in that fancy notation. F of n equals f of n minus 1 times -2, what I'm doing each time. My explicit, I can do my explicit 2 different ways. So the first way is to say, well, I'm starting at 3, and then I'm multiplying by -2 over and over and over again. Again, though, I'm going to need to fix my exponent because my first starting is f of 1, not f of 0. So I'll fix my exponent by saying to the power of n minus 1. Now the second way to write my explicit is to say f of 0 times -2 to the n power. In this case, I'm not fixing my exponent. Instead, I'm fixing where I start. So I want to find f of 0. So remember when we went forwards, we multiplied by -2. So when I go backwards, I am multiplying by -1 over 2, or dividing by -2. So then I have my first term times -1 over 2, which is -3 over 2. So now I can finish writing in my f of 0.